Welcome to OSG's Solutions for Electric Vehicles. This video's topic, the bumper frame. The bumper frame of an electric vehicle is composed of various materials. These materials can include polypropylene, fiber-reinforced plastics, ABS resins, and even aluminums. The material of a bumper frame is chosen according to its purpose. However, the bumper frame is typically constructed with softer materials. Hard materials will transfer the forces of any accidents directly to the people inside of the vehicle, and thus are unsuitable for a bumper frame. The overall shape of a bumper frame will vary by manufacturer and model, but almost all bumper frames are thin-walled with many holes and pockets. These bumper frames can be typically made from aluminum or carbon fiber reinforced plastics. They feature holes and pockets both open and closed, and therefore require drilling and milling by end mills. The size of a bumper frame varies, however, the depth of the features of the holes and open pockets can be 3 to 6 millimeters or more depending on the part feature. OSG's solution to this application is the A-brand AEN end mill. This A-brand AEN is comprised of two different series, including the AETLN and the AEVTSN. These end mills feature a diamond coating, a size offering that ranges from 3 to 12 millimeters, or 1/8 of an inch to 1/2 inch, and even 1 inch for the TLN, as well as center cutting capabilities and variable geometry for the VTSN. Application challenges of a bumper frame include many through holes and pockets. These features are most commonly machined with an end mill. Plunging into the part allows the reduction of cycle time and tooling costs by combining two tools and operations, drilling and milling, into one. OSG's solution, the AETLN and the VTSN, are center cutting, which makes drilling and milling with one tool possible. Another application of bumper frame machining is the high volume production and unattended nature require the use of tooling with long, stable life to reduce the cost of downtime due to tool changes or breakages. AEN features DLC Superhard and DLC IGES coatings, which prevent wear and welding from machining and provide longer tool life compared to other end mills. In this test example, you can see plunging done with the AETLN. The tool was a 1/4 inch diameter by 3/4 inch length of cut and plunged into a 70-75 aluminum. The tool was held in a milling chuck in a Mitsubishi Vertex BT40 taper machine, with a total cutting depth of 1/4 of an inch or 1 times D. The red boxed area shows the recommended cutting conditions for the AETLN in a plunging application. Within these parameters, the chip shape is stable, as well as the chip evacuation. When the speed and feed are elevated beyond this, the chips begin to get crush, indicating increasingly unstable performance. However, even furthermore into the red zone, the tool exhibits bird nesting and chip packing in the flutes. So as long as a customer can stick within the parameters highlighted within the green or even yellow boxes, there will be no problem with plunging with the AETLN. Similarly, these are test results shown with the AEVTSN. The tool was a 1/4 inch by 3/4 length of cut into a 70-75 aluminum, held once again in our Mitsubishi BT40 taper machine. The depth of cut was again a 1 times D or 1/4 of an inch. You can see here that we've exhibited zero unstable cutting performance across the entire range of the testing parameters, meaning there were no problems even at those elevated conditions of 656 SFM and 2 thou per tooth. This slide highlights the chip shape comparison between the TLN and the VTSN. Because the AETLN only has one center cutting flute, Even at a lower inch per tooth feed rate, you experience a larger and more thicker chip that tends to be crushed within the flutes. However, since the VTSN has three center cutting flutes, the chip shape is much more stable and less likely to be crushed. Here is an example of an AETLN in a tool life comparison. This tool was ran against a competitor DLC-coded tool as well as a non-coded tool. The application was a side milling application running at 380 meters a minute and 20,000 RPM. The feed rate was 1600 millimeters a minute. The feed per revolution on the 3-flute tool was 0.03 millimeters a tooth, and on the 4-fluted tool 0.02 millimeters a tooth, in order to maintain that fixed feed rate. The depth of cut was 17 millimeters down, and the radial depth was 0.1 millimeters over. During this operation, we used water-soluble coolant. As you can see, the non-coded AETLN showed severe chipping after cutting roughly 285 centimeters, but the AETLN showed stable wear even after cutting 856 cubic centimeters. The competitor tool also showed stable wear after cutting 856 cubic centimeters. However, there also is chipping and other forms of damage on the end mill, meaning that the quality of our own DLC coating and the cutting edge of our AETLN is superior to that of our competitor. Thank you for watching. For more information, please visit www.osgtool.com.